And so now let us pull up the so this is the beautiful 741, right. So I believe you understood what Q1, Q2, Q3, Q4, Q8, Q9 and this feedback loop is doing, correct. Okay. All right. Now, this is that IREF we were talking about. Okay. Now, there is something clever as with every one of the designer of this circuit is a guy called Robert Widler, right, and like almost all of his circuits are incredibly clever, right, and so this is an example of yet another example of a clever idea. So let's first let's assume that these op amps are all used supposed to intended for dual supply, right. I mean people use plus minus 15 volts and so on. But it does not matter. Let us just for our own simplicity, let us assume that this is 0 and this is I do not know some 20 volts. Okay. So, what comment can you make about the current through this R5? What is this voltage? 0.65. This voltage is going to be 19.35. So, basically 20 minus 1.3 is the drop across the resistance. So, basically about I would say something like 18 volts, 18 and a half volts across 39K, and this basically causes roughly about 50 microamperes, is it? Or roughly, yeah, it is half a milliampere. Okay. And more importantly, as you keep changing the supply voltage, the current through this goes on changing, because the current is simply VDD minus 1.3 by 39K, right. So, and the design was such that I mean see another thing that you have to be worried about is that you can't have so if you directly use a current like this to bias the input pair, right. So, if this IREF varies with VDD a lot, correct, what problems do you foresee in the design? If I changes, the quiescent current changes, what comment can we make about the current in the input pair? It will change. If GM1, if the current changes, what comment can you make about GM1? Changes. So, what happens to the dominant pole frequency, or what happens to the unity gain frequency? That also keeps changing, right. But what happens to the second pole? If the unity gain frequency keeps changing and the second pole does not move exactly the same way, what comment can you make about the phase margin? It will go on changing, right. So, and you can potentially have the system is nice and working for 10 volts, the moment you move it to 12 volts, then there is lots of ringing and all that stuff, right. So, you want this current to be largely independent of the supply voltage. Okay. So, so basically the idea is that so if this current is let us call this I1, and how do we get IREF here? What is I mean how do we find out what IREF is? Well, VT ln I1 by IS must be equal to VT ln IREF by IS plus IREF into phi k or R, let me call this some R4, correct. So, which basically this means that this VT ln I1 by IREF must be equal to IREF times R4. Okay. So, it is actually I mean to find IREF, I mean given I1 and R4 I mean and R4 to find IREF you will have to solve this equation numerically, correct. But if you want Iref to be something, correct, then it's very straightforward to find. If Iref is known and I1 is known approximately, then it's very straightforward to figure out what R4 is, right. So, in this case, I mean, you can go figure out R4, I think it will turn out to be a few microamperes, right. Okay. And the nice thing about this circuit is that, you know, what comment can we make about Iref? Is it going to be much smaller than I1 or larger than I1? It's going to be much smaller, because there is going to, I mean, you know, it's going to be smaller by the drop e to the power of the drop across that resistor, right. So, in other words, the drop across this resistor has an exponential effect on reducing the current, correct. So, in other words, you know, for a small, very small resistor R4, you can get a very small current, right. So, nominally, I mean, normally if you have some voltage and want to generate a current, you have to do V by R is you know is the current. So, if you want a very small current, that resistance must be very large. Okay, it turns out that large resistors are difficult to make on an IC. So, basically you wanted to get a very small, you want to get a very small current, but with a small resistor. So, this is one way, this is what this current source is called, the Widler current source. Okay, and is a clever trick to get a small current while still using a small resistance. Okay, and what comment can we make about the supply sensitivity of this current? This current is actually sensitive to supply, correct, but the voltage across you know, the voltage across the base of between the base and emitter of Q11 is largely independent, because logarithmically you know, the base emitter voltage is ln of, you know, I current, right. So, it is actually very insensitive to supply voltage. So, even though this current varies by a lot, right, this current will vary by a very small. So, this is the way to get you know, that Iref to be independent of supply and a sufficient and a small, and you know, the small current that he wants without using a large resistance. All right. So, so this part makes sense. Okay. Now, for the time being, you know, just assume that these guys are short circuits. I mean, they are very small resistors anyways, right. So, the output of Q6, I mean, again for the time being, you know, remember that in our diagram we said, yeah. So, basically the second stage is going to load the first stage, and therefore, we need a VCVS, and for the active load we simply short the base and the collector, right. So, you know, in other words, the collector potential must be the same as the base potential, right. But so, I mean, so in principle, you know, we could have shorted the collector and the base of Q5, but I'll you know, soon it will become apparent why Q7 is there, right. So, the collector of Q6 goes to Q15. Q15 is what? What is it acting like? Yeah, it is basically acting like a VCVS, okay, and therefore its job is to simply increase the input resistance looking into the base, so that the gain here is not compromised, right. So, that drives you know, Q17. These resistors, this 50 ohms is actually very small resistance, right. I'll tell you why R11 is there. and likewise Q22. So, for the time being ignore Q22, assume R11 is a short, and likewise at this point let us say, I mean these are all let us ignore R1 and R2. Okay. Now, see there is the second stage goes into, now for the time being again let us assume that this is a short circuit. Okay. What is Q13? It is simply a current, whatever current is flowing here it is mirrored there. Okay. So, basically that behaves like a current source load for the second stage. And so, the output basically is through some load resistance is this is RL, which is outside the chip. So, again for the time being these resistors 25 ohms and all that and 50 ohms, let us neglect. Okay. We will figure out why they are needed just a little bit. So, the Q14, how does that behave? It is a common collector stage, right. So, common collector stage, see normally as far as the output is concerned, I mean the output stage so far we have discussed is basically a common collector stage, right. It could be an NPN common collector or a PNP. So, now let us see what the problem is with just having a single common collector stage. Okay. So, this is the internals of the op amp. So, what is the cutoff limit for this transistor? Let us say this is the common collector. So, this is some IREF. So, what is the voltage swing at the output which will cause the transistor to get cut off? Okay, maybe okay, let me remember the load is connected to analog ground, which is VCC by 2, this is VCC, under quiescent circumstances this voltage is VCC by 2, this is RL, correct. When you apply signal this output voltage is swinging like this. What is the maximum voltage that the output can go before something bad happens to the devices? If the output voltage keeps going high, what happens eventually to the transistor? So, VCE, no, this is being driven by the feedback loop inside, correct. So, if this goes too high, what happens to the transistor? It is moving towards the saturation region. So, the what is the highest voltage the output can go before the transistor gets into the saturation region? VCC minus 0.65 is the upper limit. What about the lower limit? When the output is going low, the transistor is going into the what comment can you make about the current in the transistor? So, under quiescent circumstances this is VCC by 2. So, this current when in the negative half of the input cycle, where this output voltage is going below VCC by 2, right. What comment can you make about the current in the load? Is it flowing in or flowing out? It is flowing like that. So, what comment can you make? But the sum of the load current plus the transistor current equals IRF. So, what do you think? The transistor is going towards cutoff. So, what is the maximum output swing that is possible before the transistor goes into cutoff? Yeah. So, basically the swing here around the quiescent operating point of VCC by 2 will be IRF times RL. Okay, so let me repeat it again. So this op amp is part of a negative feedback loop, correct? Under quiescent circumstances, this is VCC by 2, which is analog ground. So this voltage is going to be VCC by 2, correct? Now when the input is in the negative half of the input cycle, when in the negative half of the input cycle, what is happening? This is going to be also VCC by 2 plus some negative thing there. We are trying to figure out what the maximum amplitude is before the transistor goes into the cutoff region. So, the transistor is just cut off, the current flowing through the transistor is 0. So, therefore, all this IREF must be flowing through RL. So, therefore, the voltage across RL is going to be IREF times RL. Okay. So, you can see that the positive half peak swing is independent of RL, whereas the negative limit is dependent on RL. Alright. So, this is if you used an NPN common source common collector amplifier at the output. Now, if you use a PNP common collector, what will happen? This is VCC by 2, this is RL. Okay. So, if the input goes in the positive half of the negative half of the input cycle, what happens to the transistor? When this voltage goes low, what is happening to the transistor? When the output voltage goes low, collector is constant, at ground the emitter is going lower and lower, is moving towards the saturation region, correct? So, what is the highest, what is the lowest voltage, what is the lowest potential there before the transistor goes into the, it's plus 0.65, right? Whereas on the high side now, what happens? High side what happens? When in the positive half of the input cycle, current is flowing that way. So, the transistor is in the danger of going into the cutoff region. So, what is the maximum swing? So, the voltage across the maximum positive voltage across the RL is basically IREF times R. Okay. So, what do we see? What is the moral of the story? So, in the NPN case, the upper limit is VCC minus 0.65, it's independent of RL. The lower limit is dependent on RL. In the PNP case, the lower limit is independent of RL, the upper limit is dependent on RL, right? What do we want? We want both to be independent of RL. So, what should we do? You connect both like this. So, this is VCC by 2. Okay. So, when the input goes positive, this transistor will push current. When the input goes negative, this transistor will pull current. Okay. But when the input is 0, what happens? But I mean, in other words, when the input is VCC by 2, what happens? no current flows, because basically if this is VCC by 2 and this is VCC by 2, both the transistors are off, because the VB is 0, correct. So, what what is done, what should be done is, you have, there are many ways of doing this. One way is to put a battery of exactly 1.3 volts, okay. So, and perhaps put V in here. So, both the transistors are at the verge of conducting. If the input goes slightly positive, then the NPN transistor will conduct immediately. When the input goes slightly negative, the PNP transistor will conduct immediately. And now, because and on the high side, the NPN transistor goes into saturation, and on the low side the PNP goes into saturation. In either case, the swing is independent of the R. Okay. So, now with this background, let us take a look at this. So, basically this is that's the NPN source follower, that is the PNP emitter follower or common collector amplifier, right. Now, this is the battery, right, and that is called the VBE multiplier for a good reason. I will tell you why. So, this is 7.5 K, this is 4.5 K. So, what is this voltage? Some current is flowing. So, what is the voltage here? Base emitter voltage 0.65. So, what is the current flowing here? 0.65 by 7.5 K. What is the voltage across the 4.5 K? Pardon? Into 4.5 K. So, what is the voltage drop you see there? 0.65 times 1 plus 4.5 by 7. Right. So, this is so as you can see, this battery is not 1.3 volts, which will cause both to conduct simultaneously, right. It is slightly smaller, so that only one of them conducts at any one time. So, the input goes positive, the NMOS transistor is pushing current, but the input goes goes low, the PMOS transistor is pulling current. Okay. So, this is the equivalent of that battery. Okay. And what do you call the CC is this is the, what is that 30 puff, is a Miller compensating capacitor. Okay. So, now the question is, why do you need all, what are these guys doing there? So, of course, I mean, it is one thing to do a toy problem in a textbook, and the other one is to have parts which basically go into go into reality. They will short, they can potentially short the output, correct, to ground, and then they will blow the IC, and then they will come back and tell you that hey, you gave me a bad IC, right. Okay. Or your part is there's something wrong with your design, right. I did a great job. Okay. So, you have to so basically there has to be protection for short circuit, right. So, how do you protect for short circuit? When you short this to grow to the negative rail, for instance, the current flowing here will be very large. You have to detect when a large current is flowing. If a large, I mean when you short the output to ground, what is happening? A large current is trying to flow, and that is going to simply burn up the transistor, right, because the transistor, most of the current is, the power is dissipated in the collector base junction, right, because that has got the large voltage across it. So, it will simply burn up this transistor. So, what they do is, they put a small resistor, right. If a large current flows here, what will happen? The voltage across that R9 will keep increasing. Once it becomes very large, then Q15 will conduct, and then simply pull out all the base current that is necessary for Q14 to operate. Okay. So, this is short circuit protection. Likewise, in this case also, if I mean for the PMOS transistor, you know, first of all, there is a resistance in series to prevent somebody from going and connecting this directly to VDD. I mean that would simply, you know, blow the device. So, there is some resistance to prevent, to limit the current to some degree, and you know, if the PMOS transistor, I mean if this voltage, so you can as well sense if there is a lot of current going to flow through the PMOS transistor, that basically means that there will be a lot of current flowing here. So, again Q22 is going to sense, is going to turn on the moment this voltage drop becomes very large and go and pull that all that current down. So, basically pretty much you know, for all practical purposes, tri-stating this whole thing, right. So, making it high impedance, so that of course, your op amp will not work, right, but the moment you remove the short, you will find that, well, you know, nothing, no harm has been done, right. Okay. So, now, so we have seen all this. Now, you know, let me come to Q7 and why it is there. So, under normal operation, Q22 will be off, Q15 will be off. Okay. So, they do not have no role to play under. If everything is working fine, they are just like, you know, insurance, right. So, they don't mess anything up. Now, the current, see, ideally in an op amp, if you put the same input to both terminals, right, what must be the current flowing out here? If the two inputs are exactly the same, if you short these two terminals, ideally, this current is supposed to be exactly the same as that current. So, this current is supposed to be exactly the same as this current. So, no current must flow out, right. In reality, I mean, you know, but on the other hand, if you let us say you did not have Q7 and you just shorted this transistor here, you can see that the current being drawn by Q15, the base current, right, is not the same as the base current being drawn by you know, by Q5. So, the here what will happen if you just simply shorted these two without Q7 being there, right, then what happens is that the current flowing here is going to be, as we discussed yesterday, you will have two base currents, you know, going into Q5 and Q6 bases. So, this current will be smaller, this current will be larger. So, net current will flow out. So, even when there is 0 input. So, that is basically like adding offset to the op amp. So, what is done is you know, basically the bottom line is that you draw exactly the same current, whatever current you are drawing here, DC current, the same current has to be drawn here. So, that is why if you notice Q15 has got 50K in the emitter, and likewise Q7 has got 50K in the emitter. Okay. And so, this basically makes sure that the current is the same, I mean, so at least nominally the offset is 0, and these two terminals, so many, I mean, of course, in spite of all this, because of manufacturing variations, there will be mismatch between Q transistors, which will cause some offset, and you know, users might want to null that offset. So, you have these two terminals coming out, okay, and you can actually add resistors to, a resistor to ground there or on this side to be able to turn a knob and nullify that offset. Okay. So, that is a quick overview of the 741, right. As you can see, it incorporates a whole bunch of things that you have not learned, right. So this is is what is called a class AB stage. Right. But otherwise, a lot of these things are, I mean, even if you have not seen them, hopefully you can understand them. The input stage is actually perhaps one of the nicest features of the 741, and it is done this way for a reason. It's not some random thing that somebody woke up and said, right, let me wear my jeans pant inside out, it will look cool, and like this is this is not like fashion, right. Right. So everything is done for a reason. There's a reason why every component is there, and this was done in the days before computer and SPICE and CAD tools and all these existed, right. So this is almost a work of art, right. I mean, it's incredibly clever, and as proven in for more than 50 years, it's basically worked nicely in the field, right. And of course, there are some more bells and whistles. For example, another common thing people do is try to, by mistake, connect the what do you call reverse the supply and ground. Okay, so there must be some protection for that. Then people will try to connect, by mistake, connect 3 to the input to this to VDD and this to ground, right. Okay. And you don't want your IC to blow, so there are some protection diodes to make sure that eventuality is taken care of, and so on. You understand? So there's some bells and whistles around this, but this is a a good this is a skeleton, and which explains a lot of things that we've seen in various parts of this course. It kind of puts many of these things together. All right. So with that, we are done with this class.